Hey guys, Mr. Wimp again. So in our last video we talked about how to actually read binary, and so in this one what we're going to look at is converting binary numbers from base 10 to base 2 or from base 2 to base 10. Okay, so that's what we're going to be looking at. What I would point out is that we have to be able to bridge the digital divide. So we have to convert base 10 numbers into binary, and then binary has to convert back to base 10, something that we actually understand. Okay, so when we're looking at our binary numbers, the easiest way to convert, let's say, a base 10 number into binary is to use successive division. And so what we'll do is we just keep dividing our number by 2. All right, so if we take the number 6, and that's base 10, and we want to convert that into binary, which is base 2, basically all I have to do is take 6, divide that by 2. Well, how many times is 2 going to 6? That's 3 times, with a remainder of 0. All right, then I have this number, and I'm going to plug this number into the next one. So 2 divided by 3, which was from before. 2 goes into 3 one time with a remainder of 1. Then I have 2 goes into 1 0 times with a remainder of 1. Okay, and then 2 can't go into 0. So basically I have a 0, a 1, and a 1. So the least significant bit, so LSB, is here, and most significant, MSB, is here. So you can do this for any number. I could do it for 1,472. It would just be a lot longer. And so the way I would write this would be least significant bit goes over here on the right, so it would be 0, 1, 1. So I'd read this as 110 would equal 6 in base 10. So this is base 2. So that's a real simple way to convert that. Okay, and it looks like this. Okay, so basically you divide by the decimal number of 2, and then if the quotation is 0, the conversion is complete. So we had 2 divided by 6 equals 3, and then this guy went down here. Oops, excuse me. That one goes to it goes down to here, and then 2 divided by 3, 2 will go into 3 one time, and you have a remainder 1. 2 will not go into 0. Okay, so that's pretty straightforward. So I can convert 6 base 10 into 110 base 2. Okay, that's pretty straightforward. So let's look at an example. So here we are with the number 26. Okay, so with the number 26 base 10, so we have 26 base 10 equals how much in base 2? Okay, so what am I going to do? Well, if we look back at this guy, we see that we just divide it by 2. So 26 divided by 2. So let's see, 2 into 26, and that gives us 13 with a remainder of 0. And then 2 divided by 13 gives us 6 with a remainder of 1. 2 divided by 6 is 3 with a remainder of 0. 2 into 3 is 1 with a remainder of 1. And then 2 into 1 is 0 times with a remainder of 1. Okay, so basically we have our LSB here, our most significant bit there. So basically we from right to left have 0, 1, 0, 1, 0, and this number is equal to 26 base 10. All right. Whoops, read that wrong. This last one here is not, this should be a 1. Okay, so 1, 1, 1, 0, 1, 0 equals 26. All right, so that is how you'd work that out. And here's what it looks like in a little prettier version. 2 divided by 26, or 26 divided by 2, then 13 divided by 2, then 6 divided by 2, and you come out with 11010. Okay. Let's do 41. 41 is the same thing. So 41 base 10 into binary. So 2 into 41 is 20 with the remainder 1. And 2 into 20 is 10 with remainder 0. And then 2 into 10 is 5, remainder 0. 2 into 5 is 2 times with a remainder 1. 2 into 2 is 1 with remainder 0. And 2 into 1 is 0, remainder 1. And that's basically it. So here's the most significant bit, least significant bit, and we end up with a 1 0 0 1 0 1. So our 1 0 1 0 0 1 is equal to 41. That's base 10. This is base 2. You always have to have a subscript. If you don't have a subscript, then what you're essentially looking at is 101,001 is equal to 41, and that is wrong. We know that. Okay. Here it is, nice and pretty. You can see the same thing going through, and then we get 41 is 101,001. Okay. Here's a couple sample problems. Go ahead and write these down and pause the video at this point and see if you can solve those. And then I'll give you, and then come back to the video and see if your solution matches up with mine. Okay, so now that you're back, let's see if your answers match up to my answers. So 13 base 10 should be 1 1 0 1 base 2. 22 base 10 should be 1 0 1 1 0 base 2. 43 base 10 should be 1 0 1 0 1 1 base 2. And 158 base 10 is 1 0 0 1 1 1 1 0 base 2. So as you can see, binary is not an ideal way to represent very large numbers. Okay. Now, as we discussed before, you have weighted multiplication to figure these out. So in other words, you have the ones place, you have the twos place. So here's the ones, the twos, the fours, the eights, the 64s, and then it goes on from there. So basically you're just squaring it, tripling it, or cubing it, 2 to the 4th, 2 to the 5th, 2 to the 6th, so on and so on and so on. Okay, so 1, 2, 4, 8, 16, 32, 64, 128, 512, 128, 512, those numbers should start sounding familiar as they pretty much match up to what you would typically see in memory. 512, then you have essentially 1 gig. It's actually 1,024, and then 2 gigs, 3 gigs, so on and so on. Okay, so basically what you look at is in the ones place. How much do I have in the ones place? I have nothing, so I have 0. And these just kind of add up. How much do I have here? In the twos place, I have 1, so this is worth 2. In the fours place, I have 1, so this is worth 4. And in the eights place, I have 0. So basically I have 0 plus 4 plus 2 plus 0 equals 6 base 10. Okay, that's how that works. So basically, you can take a base number and divide by 2 to split it out, base 10, or you can take a binary, base 2, and find its multiplications to figure out, and then add those up and figure out what that number is. So it's a pretty straightforward process. Let's look at an example. So we have 1 0 0 1 0 base 2 equals, we don't know, base 10. So in the twos place, we have nothing, so that's 0 plus, or in the ones place, excuse me. In the twos place, we do have a 1, so we have 2 plus 0 in the fours place plus 0 in the eights place. And then in 16s, we have 16. Whoops, 16. So 16 plus 0 plus 0 plus 2 plus 0 equals 18 base 10. Let's see if we're right. So let's go to the next slide. And there it is. Nice and simple. So we have 16 plus 0 plus 0 plus 2 plus 0. So here's another binary number. And I'm going to give you a minute to calculate this one out. And let's see if you can get it right. Okay, so now that you're back, you should have gotten 53. And you can see that 0 plus 32 plus 16 plus 0 plus 4 plus 0 plus 1 equals 53. Okay, pretty straightforward. Okay, here's another set of problems. I'm going to give you, take a few minutes to work these out and then compare your answers to what you get on the screen. So go ahead and pause the video right now and work those problems out, and then we'll see you in a little bit. Okay, so now that you're back, you should have gotten for your answers 6, 26, 53, and 211. Okay, so that's pretty much the basics of converting those. So we have base 10 to base 2, we use division. Base 2 to base 10, we use multiplication. All right, so that's the basic summary of what we're trying to do. So hopefully you should be able to go ahead and work on the assignment now. But hopefully that will help you to figure out what how to convert your binary into base 10 or vice versa. Okay. As a little side note, if you're paying attention still, consider base 10. Why do we use base 10? I don't know what the actual answer is, but I would propose that perhaps we have 10 fingers and 10 toes, so as a species, when we learn to count, it would be natural that we'd have base 10. So use that as you will. That question may come up later on and might be a pretty decent way to answer a question that you get. All right. Well, good luck with the assignment, and we'll see you next time.